Pac-Man application has many functionalities, one of which is the placement of the obstacle. We can either click on the grid itself to place the obstacle, or place it via entering the coordinates of the obstacle. To set the direction of the obstacle, we can simply click on the obstacle itself and use the Game Boy button up, down, left, right to set it accordingly. Using the Game Boy buttons to set the direction not only reduces our preparation time, but also guarantees that our directions are set precisely. Now moving on to the Bluetooth page. The app can be connected via Bluetooth to keep track of paired devices. Our Android application shows the status of the connection to indicate any error with the connection once paired. Upon successful connection, we can receive real-time updates from the robot and send messages. During the actual run, we can have a specific interface to show the entire grid, the location of the obstacle, as well as the location of the Pac-Man, and the logging from the robot. This allows us to focus on important details without showing any other components that is not involved. One of our more valuable features is the simulation of the robot. Our robot is able to move in 16 different directions along the grid. This allows us to mimic the movement of the actual robot, which is useful during debugging.
Our algorithm utilizes a Hamiltonian path algorithm that creates a complete directed graph of cost to move from one location to another. After getting the travel cost of the path, we can use permutation to find the shortest total cost path in visiting all the objects. To find the cost of path within each node, we use A-star algorithm. Note that HN estimated cost from current to target measured in actual distance. Example is that when the robot moves in an arc, then the heuristic is the arc length.
For obstacle detection, we calculated the robot's waypoints at 15-degree intervals to ensure coverage of its turn radius. A virtual boundary of 10 cm was established to ensure the robot does not hit the obstacles, and to account for edge cases, we expanded the maximum allowable boundaries, enabling the robot to scan images at the edges of the map. We also developed a simulator to test the pathfinding algorithm. We are able to add new obstacles and also change the direction of it. The algorithm's runtime performance is also available to us.
In our high-tech Pac-Man vehicle, we have integrated a powerful brain using the Raspberry Pi 4. This advanced system synchronizes multiple hardware components like the STM32 microcontroller, Android tablet, and algorithm with image recognition technology. Thanks to the RPi multi-threading capability, the vehicle can handle simultaneous tasks efficiently, whether it's controlling motors, processing images, or running key algorithms. With the Raspberry Pi 4, this vehicle is designed to operate seamlessly and intelligently.
So, for image recognition, we have to detect the symbol from an image. The task sounds simple, but there is a pitfall that many will fall into. Take a look at the two examples taken from the RPi camera, B and 8. As you can see, they are actually very similar to one another, and this is a huge issue. Most teams will use an object detection model and realize that their model has many false positives, resulting in high classification loss. This is due to the fact that there are 31 symbols to classify, and each symbol has the same color, size, and similar shapes. Let's look at the classification loss, which is the problem that I was talking about earlier. 0.4 against 0.08, with detection being more than 4 times as likely to classify a symbol wrongly than segmentation. Thus, we opted to use an object segmentation model, thus enabling us to correctly identify all 7 symbols in task 1.
The robot is designed to ensure accurate movement based on the instructions from the Raspberry Pi. For motor control, we use PID to reduce the error between the speeds of the individual motors to ensure that our robot moves almost completely straight. Additionally, we use PID to have ramp up and ramp down to reduce skid of the robot. For communication with the Raspberry Pi, we make use of serial UART using interrupts. This allows for more immediate response for fine-grained control, and we structure each command into just 1 byte for more efficient control. To process our IR sensor's analog data, this analog signal is sampled into a digital signal using an ADC, and this data from the ADC will be sampled through a DMA channel and then thrown directly into RAM for processing using our CPU. This will reduce the CPU overhead for data transfer from the IR sensor. To ensure accurate steering, we make use of the onboard IMU, which comprises of a gyroscope and magnetometer. We use the gyroscope for rotational velocity and the magnetometer for absolute heading. The magnetometer can correct the drift from the gyroscope, and we also use a metric filter for sensor fusion. This will help us to compensate for errors and noise.